All right, we'll start from current slide. And just a couple of things, not incredibly urgent or anything because it's already passed, but just to let you know, yesterday they had the ribbon cutting and official openings of two buildings on the Birmingham campuses. On the Birmingham West campus, this new Academic Success Center. It's where Winona, either elementary or middle school used to be. They built new buildings and moved into that, and then I guess deeded to the city, back to the city, the place where their old was, and then the city deeded it right to us, or something like that. Something happened, we got it, and that's where our new Academic Success Center is. An enormous building. I can't remember if it's 2 or 3 stories. It looks like it's 3 stories. Maybe it's only 2. No, it's got to be 3. 3 stories high, huge, wide, fairly deep, has tons of space in it, and from what I understand, there might be 2 classrooms in it. The rest is all offices and I don't know what. I haven't been in it yet. So, but anyway, that's one building, and that's just on the Birmingham West campus, because Wilson Road divides the two, and it's on Wilson Road, right on it. And then the other building is across on East Campus, and that's the second dormitory, or residence hall. They don't call them dormitories anymore. Not as large as the previous one, but still a pretty nice looking building. Okay, so they had ribbon cutting and grand official openings yesterday for both of them. Didn't get this until Monday in the mail. It probably was in there before this class, but I checked it when I first came in. At the end of the day, I checked, and there it was. So this does a lot of good. Okay. And then I guess I told you last time about the good news, bad news, right? Yeah, okay. All right. Now, I can't think of anything else announcement-wise, but we are in Chapter 11, Vectors and Geometry of Space. 11.5 is Lines and Planes in Space. And we had done Example 3, I'm pretty sure.
Yes, sir.
Okay. And we're getting ready to start Example 4. Okay. By this point in the week, I'm beginning to go downhill fast. Okay.
One thing I wanted to ask you about was, it's not really class related, but yesterday they voted on the to bring the baseball program to Birmingham.
I didn't hear that. What baseball program is that?
They were gonna. It was supposed to be like a baseball program for like underprivileged youth in
Oh, really?
Birmingham, and there was a neighborhood in Birmingham that was totally against it, and it was a pretty prominent neighborhood, and so it got shot down. But then they have somehow pushed it through. I didn't read the article, but I saw yesterday that they voted on it again and pushed it through.
Huh.
Because it was the Glen Iris neighborhood that was against it. Because I think it was what's the park right there? The name of the park?
There is a Glen Iris Park. There's a George Ward Park.
I think it's George Ward.
George Ward Park. Okay.
It's like 100 and something acres or something like that, and they were going to dedicate like 30 acres of it, or maybe not even that much, to the baseball. I just didn't know if you had heard anything about it, or if you were...
No, we used to live in that neighborhood, in Glen Iris neighborhood, but we moved to the next, I think it's the next one over or two over, Forest Park neighborhood. But yeah, those are our old stomping grounds. In fact, the house we lived in, we rented the first year and then lived about 10 years or so in a house, and we looked across and could see George Ward Park. I mean, we were that close to it. Nice area. We used to walk our dogs there a lot,
I mean, I was just trying to figure out I'm sure there's two sides to every story, but I was just trying to figure out what the problem was with it, or why they were so against it.
if you want an honest reaction to it, that's a fairly predominantly white neighborhood, and I wonder if they didn't want underprivileged kids in their neighborhood. Though it's not upper class neighborhood by any means at all. And it's
sort of like when you're in that, I mean, I thought about that, but when you're in that section of Birmingham, it's like you can go a few blocks.
Yeah.
And, you know, you're not in an all-white neighborhood anymore.
Right.
You know, I mean,
exactly.
I just didn't understand what the big, gripe against it was. But
yeah. I would like to, was it city doing it, or county, or state? Or
I know the mayor was involved. It may have been Birmingham City, I believe.
That's what I would guess. The representative from that district for decades has been our Councilwoman Valerie Abbott, and that would be who I'd like to find out what the problem was, because she's little Miss Proper stuff, and she comes across as if she's all progressive and stuff, but I just wonder where she stood when that happened, or if she stood anywhere.
Because what I read originally was that one neighborhood was sort of the one that was holding it back.
Yeah. Well, yeah, I don't know. I haven't heard anything about it. I asked my wife. She usually keeps up with that kind of stuff better than I do. And if not, she'll find out about it. She knows exactly where to go to find out. I'm glad you asked, because that's, I mean, literally, we lived within sight of George Ward Park and lived in that neighborhood. Valerie Abbott lived right up the road from where we lived. She's in a very sort of exclusive neighborhood on a closed loop type thing. Big old grand houses up there. We looked to buy one that was a little run down. That's the only way we could afford it, but then we got outbid on it. So
I actually drove through there today because I wanted to see where George Ward Park was in relation. I drove by. I googled the Glen Iris Elementary School.
Mm-hmm, yeah.
And I drove around that area because I wanted to see where George Ward Park was in relation to it.
Right there. Yeah. There's also Glen Iris Baptist Church. I don't know if you're familiar with them. They have a small radio station, GIB. Yeah. But they're very conservative. So I don't know if they were against it or not. I don't know. And they may have changed leadership many times over since we moved out. I don't know. It'll be interesting to find out. If I can remember, I'll check on that. And then if I can remember in a week and a half to let you know what I found out. That's the bigger issue. All right. Any other questions before we get going today? Okay, we're at example 4, top of page 790. It says, find the angle between the two planes, and here's a plane, x minus 2y plus z is equal to 0. Did we not do this problem?
I have.
Because I remember asking, this has to go right through the origin.
Yeah, we did. I just don't have it written down in this set before, but it says.
Yeah, I remember getting that angle.
And then we have to take the arc cosine of 0.
Yeah, we did exactly that. But I usually put a mark in place, and I don't see a mark anywhere here.
I had it written down, I just didn't have it labeled.
Oh, I think maybe we got down to the end of the problem, because I think we had gotten to, and we had, just like they did, y is equal to 4z divided by 7z, or we had those fractions in there, and then I said, or you could multiply by 7, and we came up with the same thing they got. And so I think we got that far, okay? I think we got down to the point where x is equal to t, y is equal to 4t, and z is equal to 7t. I think we got that far, because I think the first time we did it, we got all fractional forms, something over 7. I said, or you could multiply all three of these by 7, and then you came up with this. Okay. So anyway, I think we got that far. And now it says here, I don't remember saying this. This is the line of intersection between the two planes. Okay, I don't remember even saying that part either.
We may have gotten further than this. The last thing I had wrote down was to do the arc cosine of 0.594.
Yeah. Yeah, and we did that, and that's where we got the angle of 53.55 or something. I thought I remember doing that. We didn't, or did we? Or did you have to leave it?
I'm just saying that's what I have. The last thing I have written down is that.
Was that?
So I don't know.
Did you have to leave a little early last time? You did, okay. I think we got a little further. Now, the part I didn't get to say, it says, which indicates, once you have these written down, that these 1, 4, and 7 are direction numbers for the line of intersection. Okay? And that's a little bit different from the direction numbers that we use for planes. If you remember back, trying to find the exact place they give those, it's when they're talking about the normal vector. Oh yeah, there it is. Yeah. Well, I still don't see. Oh yeah, there it is. Direction number. It's the second paragraph in the section, 11.5 on page 787. It says, consider a line through a point blah parallel to the vector blah. V is ABC. The vector V is the direction vector for the line L, and A, B, and C are direction numbers. So yeah, it is referring to the same thing. I was thinking it was with the plane, but it was with the line. So these are your direction numbers. Okay? Now, here's the next thing it said. Note that the direction numbers in example 4 can be obtained from the cross product of the two normal vectors. Now, we had already determined what the two normal vectors are. Of course, the two normal vectors would be those, what I was considering the direction numbers there, for the, given. I was writing down the first one, so its normal vector N1 would be 1, -2, 1. The coefficients of that plane. The other plane was 2x plus 3y minus 2z. 3x, no. I can't remember. I have a good memory. It's just real short. Okay. 2x, okay, minus 3y, no, plus 3y minus 2z, I'll get something right here, equal to 0. And as I said, that also passes through the origin, and its normal vector, N2, is then its coefficients, 2, 3, -2. That's how we started the problem and dealt with it. But it says, note that direction numbers that you get here, you can get from the cross product of the two normal vectors. Now, didn't we do the cross? I guess we didn't, because this one didn't require the cross product. Or did we? I don't think we went that far with it. The previous example we did, but I don't think we did on this one. So let's do this. The cross product of N1 cross N2. Now remember how we did the cross product? We do that determinant thing, and we put the I, J, K, and I prefer to go on and do IJ again. The book doesn't do it this way, and it's fine. And this isn't really a determinant anymore, but it acts like one. And then you put the N1 next, because that's one listed first. 1 minus 2, 1, and then repeat 1 minus 2. And then you write N2, which is 2, 3, negative 2, and repeat 2, 3. Okay? To me, this is the easy way to do it. You don't have to keep up with signs as badly. You do the down, it seems like we did this one, but you do the down diagonal there, and you get what? 4i. Don't forget the vector part. Okay? Then the down diagonal here would be 2j. Don't forget the vector part. And then the down arrow there would be 3k. Got it. Now you do your up directions. Okay? Now remember, when you're going up, you're subtracting, but this would have been a, yeah, it would have been a minus 4k, but now it becomes a plus 4k because you're subtracting. Okay? Okay? Then the next up diagonal is going to be a negative 3i, and the final one would be a only it's up, it's going up, so it's a minus of that, plus 2j. Okay, you add those together and you get I plus 4j plus 7k, and those direction vectors there are 1, 4, I'm sorry, I hit the wrong one, 1, 4, 7, 1, 4, 7. So that's all it was saying to you. Okay. That means the line of intersection of the two planes is parallel to the cross product of their normal vectors. Parallel to the cross product, yeah. The cross product of the normal vectors would be pointing like this, and perpendicular to both of those is the line of intersection. Okay. Done. That was example 4. Wrap that up. Now, I'm not finding the verbiage here that goes along with the title here. Wow. Oh man. Planes in Space is way back there, okay? On page 788. That's the title here, Planes in Space. And it says 2 distinct planes in 3 space, either a parallel or intersecting a line.
That's weird.
Now we did do that though, didn't we?
Yes.
Okay. But I don't see this paragraph here. Ah, here we go. It's at the bottom of page 789. Okay? All right, that's where it is. We're still in the topic planes in space. This picks up there. We did the problem after they did this. So here is this. We should have done example 4 after we did this slide. Okay. 2 distinct planes in 3 space are either parallel or they intersect in a line. Now I think, okay. For 2 planes that intersect, you can determine the angle. Yeah, we already did this. I'm sure we did this. So let's move on. Oh yeah, there's the formula we used. Okay, I think this is where we belong. sketching planes in space. This is on page 791, and that's where I had a mark, but I don't have a pencil mark there, so I must have just forgotten to mark it with my pencil. So sketching planes in space doesn't sound good because we don't have a space to draw it on. We only have flat surfaces to draw a spatial line on. If a plane in space intersects one of the coordinate planes, then the line of intersection is called the trace of the given plane in the coordinates plane. Okay, of the given plane in the coordinate plane. Okay, here's what it's talking about. Okay, remember, we're going to use that as the x-axis, this is the y-axis, and this is the z-axis. So this is your xz plane, your yz plane, and your xy plane. It's the floor. Okay. Now, let's say we have a plane here. No, not like that. Okay. So, here's a plane, up like that. Okay? I'll do it like this. Where it intersects the xz plane is a line right there. Where it intersects the yz plane is a line right there. And where it intersects the xy plane is the line there. So any plane that's not parallel to one or more of the coordinate planes, that's what we mean by the coordinate planes, is going to intersect in a line. Okay? If a plane in space intersects one of the coordinate planes, then the line of that intersection is called the trace of that given plane on that coordinate plane, in that coordinate plane. To sketch a plane in space, it's helpful to find the points of intersection within the coordinate axes and its traces in the coordinate planes. Now that sounds sort of blah, 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 but actually it's not a hard thing to do. Okay? So let's consider this plane. 3x plus 2y plus 4z is equal to 12. That's a plane. How you know it's a plane? All the exponents are 1. Okay? If any one of those is a square or a fraction or anything else, any power other than 1, it's going to have curvature in somehow. This is a plane. Okay? Just like if they're all 1s in 2 space, it's a straight line. Okay? So you can find the xy trace, the xy, that's the 4 trace, by setting z is equal to 0. Because z is 0 in the xy plane. You know, it's down there. So what you do is put z is equal to 0, and that gives you a line. 3x plus 2y is equal to 12. Right there. Okay? And that's, you can easily plot this point, set y equals 0, and you have x equal 4. Okay, so that would be where y is equal to 0, x is equal to 4, and where x is equal to 0, y is equal to 6. That would be out here. So there's the line that's the trace of that plane through the xy plane. Okay? This line intersects the x-axis at 4, 0, 0, 0 because z was 0, then you just set y equals 0, and that gave you 4, and the y-axis at 0, 6, 0. Exactly what I did. So basically, you just one at a time set each of the variables equal to 0, and just keep going with it, and, you know, until you get them all in there, and you've got all the points, or some points that you need to sketch a line. Okay. So in this figure, that process is continued by finding the YZ places. So here's the first one. There's the line that's between 4, 0, 0 and 0, 6, 0. Okay? Now, what you do here then is which one you want to do next. We did XY plane. You pick one of the other two.
Let's do the
YZ plane. So then X is going to be 0, right? Okay? And if X is equal to 0, then set any one of the other equals 0. What would you check?
So it would be 6 and 3.
Second?
6 and 3 would be the...
Okay, well, you do it one at a time. 0, 6, 0, and 0, 0, 3. So 0, 6, 0 is that same point. Remember, we had that one before, and 0, 0, 3 would be right up there. Okay, that now is a trace on the YZ plane. Okay, and what plane do we still have to go?
The
XZ plane. So here you say y equals 0. 4
and 3.
4 0 0. No, wait. Yeah. 4 0 0, and then 0 0 3. Well, 0 0. 4 0 0. We already had 0 0. Oh, we already had both of those. So there, you draw that. So now that you have those points, and basically you only needed one of those again, because that one, and then you can just draw that one down. That would be, and there's the plane that does it. Okay. You shade the triangular region lying in the first octave. They don't number the other octaves, but the first one you know is plus, 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 okay? And then you do that, and you just imagine it going on back into the board that way and going on down this way. Okay. May not intersect the first octave, but this one did, and it was pretty easy to do. Okay, if an equation of a plane has a missing variable, such as this one, what does that tell you?
That it doesn't intersect.
What's that?
That it doesn't intersect.
It doesn't intersect the y-axis anywhere. It intersects the other two, but not the y-axis anywhere. So if it didn't intersect the y-axis, then it's parallel to the y-axis. Okay, it never intersects. It can intersect the xy plane and the yz plane, but it doesn't intersect the y-axis. So you're absolutely right there. So it will be, the plane must be parallel to the axis represented by the missing variable. Okay, so here's the one missing that one, so it comes through like that. And you can again set z equals 0 and x is 1/2, so 1/2 0 0, and then x equals 0, z is equal to 1, 0 0 1. So it only has one trace on one of the coordinate planes. Oh, I'm sorry. Wow, yeah. Defined by these, and then on the xy axis and the yz axis, both the ones that have to do with y, it's a constant there. Okay, and that they say the plane is parallel to the y-axis, meaning they never intersect. So how can a plane be parallel to a line? You know, that seems a little bizarre.
I was actually thinking that.
Yeah, they don't intersect. Okay, now if two variables are missing from the equation of a plane, such as ax plus d is equal to 0, then this is just x is equal to d over minus d over a. So wherever that is, that's a plane parallel. That's just the x value, whatever that is, whether it's positive or negative. I'm going to assume it's positive, and it's there. It's a plane that's perpendicular to the x-axis, doesn't intersect the z-axis or the y-axis. Okay, so it just comes out minus d over a. Now this makes it look like that's a negative number, but if either d or a, one or the other, but not both, were negative, then this would be a positive value, like it's shown here. And same thing with this, and minus b over the other. You should just calculate them. You don't need to use letters, you know, and then this would be a plane parallel to that. Okay, so this would not have a trace on any of the planes. Certainly on one that didn't include the variable, but it intersects only one axis because it only has one value that it could intersect the axis. This one intersects two axes, okay, and the other one intersected three. Okay. Now, I think that was all blah, blah, blah. No examples to do.
Well, there's. Oh, no, yeah, you're right.
Yeah. And we move on to distances between points, planes, and lines. Okay? When you're talking about distances like this, between points, planes, and lines, you're talking about straight line perpendicular distances. Okay? So I think all that will come out. Consider two types of problems involving distance in space. Finding the distance between a point and a plane, and finding the distance between a point and a line. Okay? So, the distance D, capital D, between the point Q, between a point Q and a plane is the length of the shortest line segment, okay, connecting Q to the plane. So if this is Q over here, and here's your plane down here, they don't identify it by name anywhere, but it's plane P. Oh, there it is, plane P. I thought that was P for this point here being PQ. But I guess that is what that point is, but it's the plane that contains that point P. Okay. Now, and this point, well, certainly there's a distance, but that's not the distance. The distance is the perpendicular distance. Perpendicular distance. So what you have to do is find the projection of PQ, this vector here, PQ, onto the plane in question, and then the perpendicular height there from the projection to there is what you need. Okay. So let's see if we can quantify that in any way. I did hit the whole slide, didn't I? Yeah. For any point P in the plane, you can find this distance by projecting the vector PQ onto the normal vector N. Okay, let's go back. Okay, it is projected here, but you project it onto the normal vector of the plane, then you don't have to figure out this. You're given that. That would be that normal vector, okay? The projection of this line onto the normal vector, that will be, and the magnitude of that vector will be the distance, because that distance is the same as this one. Okay. Now, of course, people at home can't see what this and that is because I'm pointing at the board. Sorry about that, folks. Okay. Not too good. Okay. For any point P, okay, yeah, we already got that. Projecting the point PQ onto the normal vector N. The distance of that projection is the desired distance. In other words, the magnitude of that. So the distance between a point and a plane, the distance between a plane and a point Q, not in the plane, is, that distance is the projection of the magnitude of the projection of PQ onto N. Okay? So how do we get that? It's the dot product of PQ and N, that gives you projection of PQ onto N. Okay? And that's a absolute value because that is a scalar number divided by the magnitude of N. Okay? And okay, that's just the formula for it. Where P is a point in the plane and N is a normal to the plane. Okay? And of course, Q is a point not in the plane. Okay. So to find a point in the plane, okay, in the plane, AX plus BY plus CZ plus D is equal to 0, where A is not equal to 0, okay, can't be equal to 0, and let Y equal 0 and Z is equal to 0. Okay, let's hold before we do that. What's a normal vector of that plane? Do you know? The vector A, B, C. Remember, that was the neat thing about plane, the coefficients of the variables are the components in the direction of that variable there. You can go back, find where that is. That's why they're called the direction. Well, I thought they were called the direction numbers, but okay. If you look at Theorem 1112 on page 788, the plane containing the point x1, y1, z1 and having the normal vector a, b, c can be represented by a times this, b times this. So the a, b, and c, the coordinates of the x, y, and z, those are the components of the normal vector of that plane. The neat thing about planes and vectors, but it's a normal vector. It's not a vector in the plane, it's normal to the plane. Okay. So, with that in mind, you know what the normal vector is, ABC. Okay? Those are components of it. Now, and it says where A is not equal to 0. Now, it's probably going to come out later. Yeah. Let y equals 0 and z equals 0 in this thing. Okay? Then that's why you can't have A equals 0, because D would have to be 0 too then, and we don't want to force that. So then you have AX plus D is equal to 0, subtract D from both sides, divide by A. So then the point, negative D over A, comma 0, 0, because you let those two, that lies in the plane. Okay? So notice they didn't give you a point in the plane. They just said, pick one. Okay? And the easy one to do is find one of the coefficients that's not equal to 0, okay, and set the other two, yz is equal to 0, and then you can find the point in the plane. Okay? It's where the point where that crosses the x-axis. If it didn't cross the x-axis, then do it for y or z, but you find one that does. Okay. So that's a point in the plane. Okay? Now, from that, here's example 5. Find the distance between the point Q, which is 1, 5, negative 4, and the plane given by 3x minus y plus 2z is equal to 6. Okay. I do a quick timeout first, because I'm a cynic, remember? Okay, being a cynic, I want to make sure this point is not in the plane. If it is, the answer is 0, because it's in the plane. Well, let's see if it is. That would be 3 minus 5, that would be minus 2, minus 8, sure is equal to 6. Okay, so that point is not in the plane. All right. Now, find the distance between that point and the plane given by this equation. Okay. Well, we need a point, and here's Daniel. We need a point in the plane. Okay? Now remember how they said get one?
Yes.
If A is not equal to 0, which it's not, set the other two equal to 0, and then what's your x equal to?
2.
2. Okay? So 2, 0, 0 is on that plane, and you see, now, if this would have been a 5 here, I wouldn't have chosen that one. I'd have done this one, because that's easier to divide. You wouldn't have a fraction. Or, pick one. This one, all three of those would have done fine. So 2, 0, 0 is a point in the plane. That's your point P. The point Q is 1, 5, negative 4. Okay, so the next thing we've got to do is find the vector between those 2 points. So that point P we chose was 2, 0, 0. Now you see how easy it was here with the numbers. Minus D over Bob, yes, yeah, forget that. Just use numbers, okay. All right. So we need to get the the vector PQ. So what is that vector PQ? Terminal minus final, minus initial.
1.
Nope. -1. Terminal minus initial, okay? The other two are easy then. 5, -4, okay. First one was hard, but the second two are easy, okay? All right. Then you get the dot product of that with, and the absolute value of the dot product of that, with your normal vector. What's your normal vector to that plane?
This is where we multiply.
Not, we're going to, but we're not multiplying now. Just get me the normal vector of that plane.
We're going to do that.
Okay, just pointed back to it. If you recall, there's that theorem 1112, or what was it? Bottom of page.
Oh, okay. It would be 3 times.
Not times. It's a vector. First component 3, second component.
So it's not that A times X minus X1.
Okay. All that you have to look for there is what's the coefficient of your X, your Y, and your Z. So that sure is as easy as?
It's 3.
Yes.
-1.
2. Got it. Okay. Now, what we do with those two is take a dot product. And then we'll take the absolute value if it happens to come out negative. So I don't care which order you do it. We're going to take absolute value anyway. So PQ dotted with N. Can you do that fairly quickly and distinctly? -3. Is that what you said?
Yeah.
Yeah.
-5.
-5.
And -8.
-8. Okay. All three of those are negative. That adds up to -16, right? Take the absolute value of it and you get +16. Right? And then you divide that by the magnitude of your N. So what's the magnitude of N? I probably shouldn't have written it there. Square root of?
Yeah, that's right. The square root of 9 plus 1 plus 4.
Right, which would be?
Square root of
14. Okay, so 16 over the square root of 14. That's the distance. Okay. Yeah, that's the distance between that point and the plane. Now, I can't think of any way to make that any simpler. Yep, 16 over root 14, they just give it approximately 4.28. Okay. All right. Now they come up with something else here. And for the life of me, I'm not seeing quite where they got this. They say the absolute value. Oh. I was thinking they had variables in there, and they're not. Yeah, it's just exactly what we did. rather than write the vector here, they write it as that minus that plus that minus that. Yeah, they write it that way and then do it. I think it's just as easy to go and do it, and then easier to do a dot product and all these letters and stuff. So we did the same thing. So the thing that I don't see right off the top of my head here is why they have that plus D in there. Because we, did we ever use that? The only place that we even remotely came close to using that was in figuring out the that point. And I still don't think we used it. I don't think we ever used the plus 6 anywhere, did we? That's your D. Or the way they wrote it was at a minus 6. So I don't see why that's even in the picture there. There may be why. Yeah, okay. Yes. So they just give a shorter version, and I think they'll give it on here. So let me just clear my scratch here, and we'll see how they work the problem, and then see if they come up with the same thing. Okay? So you know that n is that, don't we? Okay? Normal to the plane. To find the point in the plane, let x, y, and z be 0, obtain p, which is 2, 0, 0. Exactly like what you did. Then the vector, and they drew it out this way, which is what you did, -1, 5, -4. And then do the distance formula, which is a dot product of those two vector absolute values divided by magnitude of n. Okay. That's exactly what we did to the letter 16 over 14. Okay. Okay. Okay, here's what they say on the next part. This is the part I was trying to see. We never used. Okay. They said D was the absolute value of A dotted with the difference of these two, which is your X component, plus B dotted with these difference of these two, which is your Y component, plus C dotted with those two, that's the Z component. And then they suddenly did this and threw in the D there. Where did that come from? Notice they used AX0, BY0, CZ0, but they didn't use this because A times, this is a minus X1, minus AX1, minus BXY1, minus CZ1, I can't say the two letters close together, CZ1, that's not anywhere in there unless you notice that the point P that we chose, okay, was your X1, Y1, Z1, okay, and we know that if that's in the plane, A times X1 plus B times Y1 plus C times Z1 is equal to minus D. So these are all minuses, so they became plus D, so that's where the D came from. So basically, you don't even have to pick that other point. You don't have to divide by the other. You just take the A times the x0. As long as you confirm this is not on the plane, then A times this plus B times this plus C times this plus D. You're given that. You're given that. That is your numerator. That's, yeah. Because, remember, this is sliding back now. Remember when I said check and make sure that's not on there? What you would have done, we plugged in x0 here, y0 there, z0 is there, and if that's not on there, that wouldn't have equal to 0. Well, in plugging those in and adding that, you saw it was equal to 0, that's the thing you put right there. That's it. So we did that already, and then you just divide by the magnitude of that. So let's go back and just review that. All right. Oh. Oh, there it is. I lost it. Okay, there it is. Okay. So let's just plug that in. 3 minus 5, that was a minus 2. Minus 8, that's minus 10. And then move the 6 over here, make it minus 6. And that's minus 16. Absolute value of that was 16. That was your numerator. And then you divide it by the square root of that square plus that square plus that square. So you see, we had done the problem without even realizing we had done it. We went through all this, but we didn't need to. You had it done right at the beginning. Now, thing that's important to remember is that you put the D with it. In our problem, they had equal D, so you have to move the D over. So it's all on one term. Okay. So the formula for the distance between a point and a line in space resembles that for the distance between a point and a plane, except that you replace the dot product with the length of the cross product and the normal vector n with the direction vector for the line. Okay. That's a hefty sentence there. So here's what it's saying. Distance between a point and a line in space, the distance between a point Q and a line in space is, and the line is given by U as being its direction vector, okay? That distance is the magnitude of the cross product of the PQ, and you know P must be a point on the line, Q is a point not on the line. Cross product of that with the direction vector for that line divided by the magnitude of that direction vector, where U is a direction vector for the line and P is a point on the line. Okay, let's see if they can give us, whoa! They didn't give us anything here, did they? All right, example 7 comes without the benefit of the picture. So let's go back and do it here. Example 7. All right.
Example 6?
Oh, I'm sorry. Yeah, they left off 6 and 7, didn't they? So let's do example 6 first. Well, example 6 hasn't got to do with the point. Okay, that goes back to the previous one. The distance between two parallel planes. Two parallel planes, that would be 3x minus y plus 2z is equal, no, minus 6 is equal to 0. Okay, and 6x minus 2y plus 4z plus 4 is equal to 0. Okay? Now, why would you even guess that those two planes were parallel?
Is there multiples?
Yeah, okay, take just the normal vector, which would be 3 minus 1, 2, and 6 minus 2, 4. Yes, they're multiples of each other. And that means they're parallel to each other. So, gotta be. Okay, so if the two normal vectors are parallel to each other, the two planes have to be, as long as they're not the same plane. Well, how do you check that? These constants are not the same, or this constant is not exactly 2 times that constant. If it were, they'd be the same lines, I mean the same planes. But since they're not, they're two completely separate planes, but parallel to each other. Okay. So, what you have to do here then, you've got a picture in your text, and it's the same thing as before. In fact, that one plane is the same plane, isn't it? Is it? Yeah, there it is. I was trying to find it. 3x minus y plus 2z. They wrote before equals 6. Now they're saying minus 6 equals 0. Same one, so it has that same vector. So we need a point on that. Okay? Well, again, pretty easy. Set yz equal to 0. You have x equal 2. Okay? So the point 2, 0, 0 is a point on that plane. Okay? Now, I'm sorry. We're doing the distance between two planes. So, not what we were just doing, what we went over more recently. So, we want the distance between that point, 2, 0, 0, and this plane here. Okay? Now, I'm real tempted to divide everything by 2, but let's not. Let's just leave it like it is. See what happens. Okay? So there's a point. The question is that point on that plane? Remember, that was the question we asked ourselves before. And how we checked that was, before they gave us a point and we plugged it in. This time we chose our point and we're going to plug it in there. And what would that give you?
X equals 12, 0, 0 plus 4 is 16.
Okay. 12 plus 4 is 16 again. Okay. Wow, you're liking 16. I don't see any reason that would have to be that, but it is. So the distance between them is 16. There's your numerator. And then we just divide by the magnitude. This time we use that one. So again, the distance they use. I'm sorry.
Where did we get 16 again?
What's that?
Where did we get 16 from again?
Okay, we picked a point not on that plane. Okay, and we picked the point 2, 0, 0. Just by setting these. It's on this plane, but not on that plane. Right? Okay. And then, that's where we got this point. It was just an easy point to get. And then they do distance. Now, what I haven't figured out is why they keep using capital D. In most of the life before now, distance was little d. But now it's capital D. I don't really know why, but we'll put a capital D because they've used a capital D. And what was it? When you plug this point into that value. And that was 16. Magnitude of that anyway, absolute value of that. Okay? Then you do it, divide by the square root of 36 plus 4 plus 16. So that's 16 divided by the square root of 56. Is that right? I'm doing it fast in my head. 56. Okay. Now, yep, that's exactly what they got. Now, you can reduce this a little bit because 56 does contain it, hidden in there, a perfect square. 56 is 7 times 8, right? And 8 contains a perfect square of 4. So let's factor out a 4 from that. So you'd have 16 divided by square root of, okay, square root of 4 is 2, so that goes on the outside. And what's left on the inside, divide 4 into, because inside there is 2 squared, which is 4, into that, and you would get 14. Okay. Now, that's not too surprising either. Everything here was doubled from that, so this is twice the magnitude. So this will be 8 over root 14. Very similar denominators, but different numerators. Okay. Goodness gracious. All right. And that would be about 2.14, which is exactly half of what the other one was, just by happenstance. Well, not quite. Okay. Then we hit theorem 1114, and now we're ready for example 7. All right, to erase?
Yes, sir.
Okay. Now, find the distance between the point Q, which is 3, -1, 4. And you see that's the point because it has parentheses, not a vector, which would need angle brackets. Okay? So that's a point P, the point Q, 3, -1, 4. And the line, and here's the line, x equal -2 plus 3t. Y is equal to -2t, and z is equal to 1 plus 4t. Okay, it's been a while. Excuse me. Goodness gracious, I'm so tired. This part of the week, it just seems like I'm losing sleep every night. So by this time of the week, I'm just worthless. Okay. Now, let's remind ourselves what that line represents. So if you go back to the very first of the section, on page 787, lines in space, a line parallel to some vector v, ABC. The ABC are your coefficients here of your parameter. 3, -2, 4. Okay? So that's your direction vector, I think is what they called it, is the direction vector for the line. In our case, 3, -2, 4. Okay? And you might say, what's the -2, 0, 1? That's some point that's on that line. Okay? That's all that really means. Okay. So we have our direction vector then, and they named that, they called it in their theorem U. This is not a unit vector, direction vector, and this will be 3, -2, 4. There's a direction vector U that is parallel to that line, in the same direction of that line, and they say this is from a point Q and a line in space. Now P has to be some point that's on the line, right? Okay. Well, I just gave you one, didn't I? The point P would then be what?
-2, 0, 1.
0, 1. Perfect. Okay, so now we need the vector PQ, which is, this is a vector now, angle brackets.
Now we would say, would be 5,
Right,
-1,
right,
3.
3. Perfect. Okay, now you got the U and you've got the PQ, and it really doesn't matter which order you do the cross product, because you're taking the magnitude of it anyway, but we'll do it the way they did. So we're going to do the cross product of PQ cross U. Okay, and that, again, you set up your determinant-like structure, and you put the I, J, K, and repeat the I and J. Okay, and you don't really need those lines here because this isn't a determinant. It's just like a determinant, though. And the PQ, I'm so sorry, is 5 minus 1, 3, and repeat the first two, 5 minus 1. And then the U part is 3, -2, 4, and repeat the 3 and -2. All right? Now, how do you find this vector?
Is -4, -4i.
Okay. Minus 4i
And we have 9j.
plus 9j
And minus 10k.
Got it? Okay. Then do your up diagonals.
A positive 3k.
Yep.
6i plus 6.
Plus 6i.
And negative 20j.
Okay, yeah, I'm trying to get my pen. Yeah. What do you say?
Negative 20.
Oh, I thought you said -1. Okay. Minus 20j. Okay, got it. Okay. Combine those, and what do you get?
2i minus 11j minus 7k.
17k. Okay. No, 7k. I thought you said 17. I thought, where did you get that? Okay. 7k. All right.
Doing Common Core math.
What's that? Yeah, Common Core math. Okay.
Which I heard they are repealing, or they're going to vote to repeal it.
Who is they now?
The state of Alabama.
State of Alabama. Not at all surprising. How much more backward can we go? Okay.
Right.
Okay. Well, I'll be quiet. Okay. And what we need is the magnitude of that vector. And what is the magnitude of that vector?
The square root of 4 plus 121.
Yeah, 121.
Plus 49.
Whoa, big number, huh? That's 170 plus 4 is the square root of 174. Okay? That's your numerator. And your denominator is the magnitude of your U vector, which we have there. And the magnitude of U is equal to the square root of here's U
And then 16
plus 16. So that's the square root of 29, if my math's right. So we do the square root of 174 over the square root of 29. 29 is a prime number. So unless 174 is a perfect multiple of 29, which I don't think it is. It may be. Is it 5? No. That's not 5. Okay. 6 maybe.
No.
No. Okay.
Oh, yeah, it is. You're right.
It is 6. Okay. So that's the square root of 6. Which, whatever that is. 2.45 approximately. All right. So that's the distance between there. Now, I think we did it the same way they did. And it's not on the slide set anymore. So that finishes 11.5. Homework exercises here are number 5. That should be a Calc chat. Oh, was there a question? Oh, I thought you said something. Okay. Any of the odds 7 through 11, they're all at Calc chat. 9's at Calc view. Either 13 or 15, they're both at Calc chat. 15's at Calc view. Any of the odds 17 to 23, they're all at Calc chat. 25 or 27, they're both at Calc chat. 29 or 31, they're both at Calc chat. 33 or 35, they're both at Calc chat. 37's at Calc chat. Any of the odds 39 to 43, 39's at Calc chat. Any of the odds 45 to 55, they're all at Calc chat. 47's at Calc view. Either 57 or 59, they're both at Calc chat. 61 or 63, they're both at Calc chat. 65 or 67, they're both at Calc chat, but 65 is also at Calc view. Any of the odds 69 to 73, they're all at Calc chat. 75 to 81. Yeah, 75 to 81. I got lost there. They're all at Calc chat. 79's at Calc view. And either 83 or 85, they're both at Calc chat. And keep on going. In either 87 or 89, they're both at Calc chat. 87's at Calc view. 91 or 93, they're both at Calc chat. 91's at Calc view. 95 or 97, they're both at Calc chat. 95's at Calc view. 99 is a Calc chat. And you can explore doing 101 or 103, or think about 103 anyway if you want to. That's up to you. If they're in there, they should be at Calc chat. And there's a modeling data 105 that should be at Calc chat as well. A distance problem 107, point of intersection 109, finding parametric equations 111, and a few true false 1. Let's see. All right. Any of the odds 107 through 111, they're all at Calc chat. And true false was 113. Any of the odds 113 and 117. And they should be at Calc chat. There's a section project if you want to look at it. Knock yourself out. All right. Now, I told you one thing before, and I'm changed. Okay? I was going to be making out the test, and when I went through, I found a test for this class that I'd already done based on chapter 11. It was another term. We hadn't gotten the first part of 11 done, or we hadn't done all of 11, so we went back and started there, and that was the first test we did. So I included 11.6 in that. So 11.6 will be on your test, so let's get started on 11.6 now. Do we have time? I mean, no?
18 minutes.
18 minutes. Let's get started anyway. Yeah.
Ask a quick question.
Okay, sure.
Well, this may be for another day.
What's that?
It may be for another day, maybe before class one day.
Well, you can go and ask it. It's fine.
Well, I was just, I have a friend that has a 7th grader.
Has a what?
Has a 7th grader.
Yeah, okay.
And both of my friend and his wife are fairly educated, but they struggle with her math homework because it's a Common Core and don't know how to do it.
Uh-huh.
And so I was just going to ask your opinion on what the benefit of using Common Core is over the old, just knowing that it's like, 5 times 5 equals 25, but for them it's like from what I've read online about it, it's like it's supposed to teach you why, instead of just memorizing that 5 times 5 is 25, it teaches you in a different way of thinking about it, that there are 5 5s in the number 25, it's kind of.
Yeah. See, I don't know beans about Common Core. I just know politically it's tossed around like a football. Now, the only thing I could think of when you said that, you might say it's 5 times 2, which is 10, plus 5 times 2, which is 10, plus 5 times 1, which is 5. 10 plus 10 plus 5 is 25. Now, that's one way to break it down and make it make more sense to me, but I don't know if that's how Common Core does it.
Well, and see, I'm, here I am in a Calculus 3 class, and I was getting confused on some of her, because they're like word problems. And
right.
I was getting mixed up on some of her stuff, and like my friend hasn't been in college in 10 or 15 years, so he just, I don't know, I just think it's I don't understand that I'm sure there has, there has to be some benefit to it, because otherwise, they wouldn't have just done it, but.
Well, I don't know. I just know, if my memory's right, Common Core was a thing that, guessing it was George W. Bush's administration came out with, trying to, I think it was in conjunction with No Child Left Behind, and it was going to get everybody doing the same thing in all the fields of study, not just math. And so they came up with it, and then once people started trying to use it, they didn't like it because it was different from what they had done before. And then suddenly it got blamed on, I hate to say this, on the Democrats, and it became a Democrat thing, so therefore all the Republicans were against it. Now that's what the perception of it is, and that's all I know about it, and my perception may be wrong. I don't know what the actual things are, but I remember when I was in school, it was called modern math. And of course, all the teachers hated it because it wasn't how they had already taught or anything else. And it was sort of bizarre, mostly because it was different. So I don't know, it's just rehashing it seems like to me it's rehashing the same old, tired arguments. And the thing is, if you just, the more I study math, the more I see all the connections in it. So I bet you I could look at Common Core and not be maybe as confused, but I might be saying the same thing I do sometimes about this. Well, why are they doing it that way? I can see it's right, but why? What's the point?
And like I said, from what I've read online about it, it's supposed to, instead of just memorizing the 5 times 5 is 25, it's supposed to put things in more of understand where you are on the number line better, and from what I've seen, it's dropping us even further worldwide in the rankings, because nobody is able to, my friends don't know what to do to help their daughter with homework because they don't understand it,
Oh man, that is a mess.
Yeah.
All right. Do we still have any time left?
Oh, yes, sir.
Oh, we still do. Okay. I just don't know enough about it, except it sounds like it's a huge political football that keeps getting bantered back and forth, and to me it's...
You got 13 minutes.
So what?
13 minutes.
13 minutes. All right. 11.6 is, we're still in chapter 11, Vectors and Geometry of Space, and this is the last section we'll do, Surfaces in Space. We'll recognize and write equations of cylindrical surfaces. That's pretty straightforward. We'll recognize and write equations of quadric surfaces. That's actually the first thing, one of the things listed under Cal 3, quadric surfaces, even though the rest of it was here, it's there. I don't know why they put it together this way, but they did. And we'll recognize and write equations of surfaces of revolution. Excuse me, I've got the hiccups. So let's start with cylindrical surfaces. They say, you've already studied two special types of surfaces. One is a sphere, and I don't recall specifically we did this, but probably we did. And this is one way to write that. X minus x0 squared plus y minus y0 squared plus z minus z0 squared is equal to some r squared. Where the x0, y0, and z0 is the center of the sphere. That's a point at the center. And then the key thing here is that all the coefficients here are the same in both. They're all plus signs. And that's equal to r squared. And what I like to do anytime I'm dealing with that is to write it in a slightly different form, and you might say, why is he doing that? And that would be probably a good question. But let's divide everything by r squared. Okay, so this becomes 1. So anytime you have something that's a perfect square over perfect square plus perfect square over perfect square with same coefficient, perfect square over perfect square, same coefficient, the square root of that denominator, the common denominator, is your radius, and the point, the x0, 0, y0, z0 is the center, and that's going to be a sphere. The plane, say they wrote equal 0 rather than equal 1, but that's the one we just dealt with earlier. What makes a plane is the fact, and this is three-dimensional plane, not 4, 7, 8, or 10, or even two-dimensional plane. That's just a plane. Okay, this is three-dimensional, and each of the exponents is raised to the first power. They don't necessarily have the same coefficients, nor would you expect them to. The A, B, and C, though, are the normal for that plane. We just did that. Okay, they're the components of the normal vector. Third type of surface in space is called a cylindrical surface, or simply a cylinder. Now, what pops into my brain when I think cylinder is a tin can of tomatoes or beans or something like that you get from the store. But that's a very special kind of cylinder, a right circular cylinder. Okay, that's very special. It's another special kind that it's a closed cylinder. Okay? Now this would be, or at least the base of this, if it didn't have these notches in it, that would be a cylinder too, but it wouldn't be right circular. Somewhat right, but not circular. Okay? Somewhat of a square base. Now this part in here is circular, but this part out here is not. So that would be a cylinder. Okay, I can buy that. Okay? To define a cylinder, consider the familiar right circular cylinder, which we all think of, my tin can, shown in this figure. The cylinder was generated by a vertical line moving around a circle, x squared plus y squared equal a squared. Okay? In the xy plane, that made the right circular cylinder. Now, technically, theoretically, it extends infinitely in both directions. So it's not a tin can. A tin can is a segment of a right circular cylinder. Okay? But that, you see, there's no limitation on z, so z can go from positive infinity to minus infinity. Minus infinity to positive infinity. Okay? The x's and y's are constrained to be within the limits they have there, depending on how big the A is. Okay, so there is a right circular cylinder. And my point is that's a closed cylinder. here is actually the definition. This circle, the circle that we had there was the generating curve for a cylinder as indicated in the following definition. Definition of cylinder. Let C be a curve in a plane. Notice what they did not say. They did not say a closed curve in a plane. Just a curve in a plane. Let L be a line not in a parallel plane. The set of all lines parallel to L and intersecting C is a cylinder. The curve C is a generating curve, or sometimes called the directrix of the cylinder, and the parallel lines are the rulings. So if I were to take a marker and just draw any old curve on the floor here, okay? It doesn't have to be a closed curve. Okay. Then I take any old line. Now if I did a line perpendicular to the floor, that would be a right cylinder. Okay? It wouldn't have to, it could be the floor wall line. No, I'm sorry, we won't go into that. Okay. But that would be a right cylinder. But guess what? The line could have been like this. And as long as I stay parallel to that and follow that curve, I've just done a cylinder. That wouldn't be a closed cylinder. It would be a right cylinder, okay? Or a right closed cylinder. So a cylinder could be any of those things, okay? All you needed is a curve in a plane and a parallel line not in the plane, okay? Not parallel to the plane, okay? Not in a parallel plane. So it could be a line up here that couldn't trace that curve at all, okay? It has to be a line. Then all the summation of all the lines parallel to the L that follow the curve, that's your cylinder. Without loss of generality, we can assume that C, the curve, lies in one of the three coordinate planes. It wouldn't have to. It could be a plane that goes up like this, you know, just have a curve on that, and then it could be all sorts of things. So, but let's just assume it's in one of the coordinate planes. So here they've drawn one. The curve is in the XZ plane. No y dependence on it at all. Okay? Then your line, it doesn't have to be parallel to the y-axis, but it looks like they did one. So this will be a right cylinder, but it won't be a closed cylinder. And then those lines follow that curve. Okay? Moreover, the text restricts the discussion. We're going to restrict ourselves to right cylinders. Cylinders don't have to be right cylinders, but we're going to do it. Thank goodness. Okay. Cylinders whose rulings are perpendicular to the coordinate plane containing the curve C. So now all of ours are going to be right cylinders. Notice that the rulings intersect C and are parallel to the line L. There's it. Okay, I was trying to find out. They're all parallel to L, and they all intersect the curve C. That's the definition of cylinder. Is it time?
Okay, close.
Okay.
Yeah, you got
5 minutes? Okay, good. For the right circular cylinder shown way back, the equation of the generating curve was this x squared plus y squared is equal to a squared. That's a closed curve, so it'll form a closed cylinder. To find the equation, and since we're limiting ourselves to right cylinders, so we're a right circular cylinder. Okay? To find an equation of a cylinder, note that you can generate any one of the rulings by fixing the values of x and y and then allowing z to take on all real values. That's what I just said. In this sense, the value of z is arbitrary and is therefore not included in the equation. Any z you want to, you can put in there. It's not going to change that at all. In other words, the equation of this cylinder is simply the equation of the generating curve, and that's it. Understood, it's a three-dimensional figure, because if you just look at that, your assumption is that's a circle in a plane. They say, no, it's a three-dimensional figure, so it's that circle in the plane extending in z infinitely in either direction, wherever your z is. So, equations of cylinder. Equation of a cylinder whose rulings are parallel to one of the coordinate axes contains only the variables corresponding to the other two axes. Okay, if it's parallel to z, there are no z's in it. If it's parallel to y, these are all x's and z's. Okay, and so forth. So let's sketch a cylinder. Okay. What would be z is equal to y squared? Okay. I hate sketching these things. Okay. I'm going to say that's the z-axis. Okay. And I'm going to say there's the y-axis. And then I'll say this is the x-axis. It's not a very good orientation, but it's the best I can do. Okay. And z is equal to y squared. So we're only in the yz plane, not in the x plane. And in the yz plane, this is a parabola, right? And the z is never negative. Y can be positive or negative, but z is never negative, so it's going up like this and like this. That's it. So then all the lines that are parallel to the x-axis that go through this, I'm not doing parallel lines too well here, okay, that follow that, that's going to be it. That's going to be a down the x-axis, okay. The base of it, the vertex is on the x-axis, and it's a sheet that goes infinitely up in a parabolic shape. Make sense?
Yes, sir.
Okay. Let's see if that makes sense here. The graph of that is a curve, blah, blah, parabola in the YZ plane. And there it is. Almost as pretty as mine. Hey, leave that alone. Okay. All right. If you find out anything about Common Core, let me know. Okay.
Yes, sir.
Yeah. All right. And by the way, have a good spring break. Oh, you weren't supposed to leave without your test.
All right.
We didn't get to finish 12 whatever.
Common what?
Common Core math.
That's we were talking about it earlier. Okay. I'm getting closer. All right. Now this says test 1. It's your test. Okay. Now we have done 1 through 6. We haven't done 7 through 10. So don't worry about 7 through 10. We'll do those later. So you can at least get started on that.
Yes, sir.
So 1 through 6.
Yeah. And once we finish this section, you can do 7 through 10. Because what we've done so far in this section isn't touching anything in 7 through 10. Okay. Because we're just getting started.
2 weeks.
All righty. Yeah, close to it anyway.
2 weeks.
Well, next week is spring break week.
Yeah, I get
So,
that.
yeah.
But
So, yeah, unless he's going to be absent next Monday. That's the thing he meant. I won't see you next week. It'll be the second week. I think that's what he meant, but I don't know. I hope to see him in 2 weeks, but I hope to see him 2 days before 2 weeks. Okay.